Our next speaker is Taig. He will be talking about compiling conformant probabilistic planning problems into classical planning.
Thanks. So hi everyone, good afternoon. My name is Ran and I'm going to present joint work with my advisor Onan Brafman, both of us from the Ben-Gurion University in Israel. And the subject is how to compile conformant probabilistic planning problems into classical planning. Much shorter, we deal with the question, can classical planners deal with probabilities? So the outline of this talk, I will start with some introduction of basic notions, then I will overview some previous work and the challenges that we face in this area. Then I will describe our translation or compilation into the classical framework, a small discussion on the classical side, what weights in the other side, and if time permits, I will conclude with some optimization and results. So the problem we're dealing with is known as conformant probabilistic planning. In short, I will call it CPP. And in this problem, we want to find a plan, a fixed sequence of action, not a policy. But the initial state is given us as a probabilistic distribution, as a belief state, and not as a plain state. And we wish to map this initial probabilistic distribution into a goal state and do it with a high probability. Okay, so not for sure to achieve the goal with certainty, just with some given parameter of required probability. And our solution to this problem is to compile it into the classical framework because of all the really nice, really quick planners that exist today, and try to cope with this problem. We investigated a few variants, and our most successful results were achieved with actually with the cost-bounded planner that was discussed earlier today, happily. So more formally, the CPP framework extends the classical framework, and the main differences are, of course, the initial belief state that is now a probability distribution, and this parameter theta, which is the acceptable goal satisfaction probability. It means that we need to achieve the goal with probability higher or equal to theta. Another important note is that actions can be, we assume for now that actions are deterministic, okay? So this work assumes deterministic action. It can be extended, the model can be extended easily to stochastic actions, and some of the actions can include conditional effects, and the meaning of conditional effects that some effects might be conditioned with a set of effects. It's not a precondition. You can execute the action, but if the conditions weren't all, then the effect will not take place. So I will work with this nice and very simple example. So we have this nice robot and this magnet, and for some reason the robot needs to bring the magnet into some location G, a goal location. We don't know the initial location of the magnet. It can be in either of those three spots over there with those initial probabilities. And let's say we want to bring the magnet to the goal with probability of at least 0.5. So in this example, the robot can execute two kinds of action. One is to pick from a location. If the robot wants to pick from a location and the end is free and the magnet is at the location, so everything is okay, the magnet will be picked up. But if the magnet is currently in the robot's arm, it will drop it at the location. The other one is there's a simple put in a location action, which means that if you hold the magnet, you will drop it at the location. So it's easy to see that the robot or the agent needs to figure that he should map should find a way to bring the magnet to the goal, assuming at least from at least two possible initial locations, and from the other side, you shouldn't plan anymore because it's wasteful to find a way to bring the magnet to the goal from the all three locations. So A good question here is about motivation, because it's not such an intuitive problem, and our motivation, at least, is that conformant or conformant probabilistic problems is a very simple form, or even the simplest form of probabilistic planning models. It's complicated enough, so we're trying to cope with the challenges here first, and hopefully to extend this work to a more complex probabilistic models in the future, including stochastic action and maybe sensing action too. So a bit about what was done until now in this area. There were some attempts to reduce the problem to constraint satisfaction models and SAT solvers. Later and until today, the dominating planner is the very, I think, nice planner of Jorgen Carmel from 2006, PFF. And PFF used a SAT model to implicitly represent belief state, and then some weighted model techniques in order to reason about the goal probability. And yeah, they had some really nice results, and on most domains they were the state of the art. So PFF represents a very common approach to planning under uncertainty in general, and in this area specifically. And this approach can be named as belief space search. So in this approach, we just look at the belief states as our state space and trying to find our way in this space. And the problems are pretty obvious, I think. One is that the belief space is huge in most cases, and the other one is that attempts to cope with those state spaces with the heuristic approach that was so successful in the classical side was not so good at the other side. So the question we need to deal with is how can we implicitly represent this huge state space? How can we capture probabilities? And do we need to deal with heuristics? Because earlier attempts to apply classical heuristics into the belief space were not so successful, and also some attempts to develop specific heuristics for this space were also not so successful. So now to our research, and our research was triggered actually by the very impressive and I think famous work by Palacios and Geffner, later by Geffner and by Albora and Geffner, the work around translation-based approaches to conformant planning, to contingent planning. The main difference between their work and our extension is that we're dealing with probabilities, with numbers. Another development that helped us a lot is the appearance of many cost-bounded planning algorithms the last few years, which we actually used as our classical planners. So the main idea behind the translation-based approach is very simple, in opposed to the algorithm itself. But the idea is simple. So we compile a conformant problem into a classical one, and then we just want to solve it using an off-the-shelf classical planner. The main idea behind cost-bounded classical planner, for those of you who were not here a few times today, so the classical planning setting is extended with some constant C, and we want to achieve the goal as fast as we can, and we want the plan to meet this cost bound. And a hint for the future is that we set this cost bound to be 1 minus theta, which is the sum or the probabilistic weight of all possible initial states that we are allowed to ignore or not to plan from, and still manage to find the required plan for our problem. So what's our contributions here? So mainly the contribution is showing how to extend those approaches to deal with probabilities, the translation-based approaches, the ideas Another advantage of our algorithm that it is really flexible, okay? So we can actually, for many conformant domain, we can, for many benchmarks, or for we can try and adjust our planner to many classical models, okay? So actually, we tried with the metric models and resource constraint planning and cost-bounded planning, and it is really easy to do those adjustments to our original algorithm. So our method actually uses the classical planners in order to reason about probabilities. This is a very interesting point. We implicitly do this reasoning, and this is really, and by doing this, we avoid the need to repeatedly try and reason about the goal like in earlier approaches. And we don't need the try and find out how to adjust the heuristics for the new problems. So another advantage is that our methods are really less complicated than the nice but very complicated mechanism of PFF to do this probabilistic monitoring. And another important point is that our experimental results are competitive with PFF on most of the domains tested. So for those of you not familiar with the ideas of translation-based approaches, let me try and really present it in a very simple manner. So the core of all those translation is the new set of variables. And this new set of variables will allow us to get a propositional representation of belief states. And to understand the meaning of it, let's take a S, which is a possible initial state. And a possible initial state in our case is a state with an initial probability higher than 0. And let's take some original variable L. For each of those couples, we create a new variable named L given S. And ideally, we would like that L given S will hold at the new classical problem if in the original problem and given the same sequence of action, L would have held given that S was really the initial state. And in addition to those variables, we had another set of variables and we maintain the original set of variables to represent certainty. So if L holds, it means I know L. I know it for certain, not under some likelihood. So our new set of variables is just those L given S for each possible initial state, each original variable L, unified with the original set of variables. And the intuition behind this is that we get an explicit propositional representation of the belief state, and we can condition those, we can condition on those initial assumptions to understand our current knowledge during the process. Okay, so not only our knowledge about the certain variables, but also about the probabilities, and the most important thing about the probability of the goal. More formally, we say that the probability of a proposition L in a belief state B during the process is the sum of the initial probabilities of all states that we know that L now holds, given that those states were the initial states. So by using this formula, we can actually be aware to the current probability of each of the proposition, and by that reason about the goal. Our new initial state will contain all the valid assumptions we can make on the on the initial state given the original problem. The key idea about the modeling probability side is the observation that in order to solve a conformant probabilistic planning problem, we actually need just to figure out or to find a set which is sufficiently likely. And then we can, and if we have this set, we can actually just solve a conformant problem from this set. Of course, no free lunches, and it's really hard to find such sets if the problem is interesting enough. So what we actually trying to do is to make this identification process part of the classical planning process. So the planner will decide what states it will ignore and will maintain the set which will be sufficiently large in terms of probability, and by that we can solve the original problem. Technically, so let's get in really high-level technical details. So we had two kinds of action. For each possible initial state, we had an action named drop S. And drop S means ignore S. Do not plan from S. You don't need S in order to achieve the required probability. The other kind of action is assumptions. Okay? Assumptions can be made over a possible initial state S only if the drop action was already applied. Okay? So if I decided to ignore S, I can add conditional knowledge based on these assumptions without really do the planning for it. It's important to say that the idea of those kind of actions was first introduced in another context by Albora and Geffner, and I think even earlier in the context of soft goals. So we have four kinds of actions, those two that I just mentioned. We modified the original action in order to use them as knowledge propagators. So if I know C given some assumption S, I have original effect C to L. So now I can tell that if I know C, assuming S was the real initial state, after the action is applied, I know L given S. And we have merge action that I will explain soon. The important point here is the costs. So all actions are zero-cost action, besides the first one. In order to drop an action, I have to pay. And how much do I pay? I pay exactly the initial probability of S. This is the thing that will help me to monitor how much states I'm ignoring and if it's allowed in order to solve the problem. So what are those merge actions that were introduced in actor and actor work? So we say that an agent knows phi if he knows phi under in all possible word state in this belief state. And such knowledge can be added by those inference actions that we call merge action. And these actions do not actually change the state of the word, but just deduce new knowledge given all the current assumptions. It's easy to see it by this simple formula. So let's say I have k assumptions, or to think about it easily, k possible initial state. Let's say the first I minus 1 were achieved by real planning, and the other one were achieved by those spatial actions. But the planner now assumes that he knows phi under all possible assumptions, and he can deduce this new knowledge. Okay, so after so besides the compilation, one must deal with the classical side, because just putting these compiled problems into the first planner you see in the store seems to not work so successfully, and this is because very specific properties of the compiled problems. One is conditional effect, and conditional effect is a real issue in classical planners. And in our compilation, it's our most important tool in order to do this reasoning by cases. In our compilation, zero-cost plans might exist, and zero-cost plans, we don't want them. They don't teach us much, and classical planners do not deal well with those plans. And our problems are typically large. So how do we deal with the technical issues? For now, we're just trying to use the existing tools. So we use the FF as the underlying heuristic, and FF supports really well conditional effect. And in order to deal with those zero-cost plans, we actually add some epsilon and not use real zero-cost action. Maybe I will skip this slide because this is a bit deeper discussion. I will just say that the algorithm that works best for us is a cost-bounded algorithm based on those distance-to-grow, cost-to-grow notions presented earlier today by Wheeler. But we actually adjusted their algorithms a bit in order to deal with the rationale of our problems. We want the planner to ignore as much as he can, and then realize the set of initial states that E should plan from, and then start and plan from those states, ignoring the cost. So we really want the cost-based heuristic to play a role until the stage that we know that we recognize what set of initial state we want to deal with, and then ignore this set. So if we'll be back in our robot example, so the classical plan here is to pick the magnet from the kind of red location there, put it at the goal, then pick it from the orange location, put it back at the goal. We achieve the goal with sufficient probability of 0.6, and then we can just ignore the third possible initial state. Our plan cost is 0.4, which stands in the probabilistic bound, or the cost bound that in this case set to 0.5. Yay. So a word about optimization. We must optimize. Okay, so behind this set of variables, if we don't optimize, so in most cases the compilation will be exponential and won't be useful. The good news, we do optimize, but it's really a delicate thing to do. We actually try to extend some of the nice work done by Hector and Hector on the tags and merges methods, but things become a bit more subtle in the probabilistic settings. You can find details in the paper or in the poster session right after my talk, or after those two talks after me. And a word about experiments. So we implemented this planner. We implemented a few variants of planners to deal with this stuff. We call it PCBP, Probabilistic Cost Bound Planner. We compared it to PFF. Results are mixed. On most cases, one of our planners is better. I mean, or the metric one, or the resource-constrained one, or the cost-bound one, which is the most successful one. We found that PFF is quite sensitive to longer plans because of the need in repeatedly reason about the goal. And the minus on our approach maybe is that the compilation itself takes a bit time, and in simple domains it might be a big overhead. So here is some of the results. PRP is the resource constraint planner we implemented. PFF is the one by Carmel and Jorg, and PCBP is the cost-bounded planner. And those age domains are actually domains that were modified in order to require longer plans and more complex reasoning about the goal. Okay, thank you very much.